When you first start Centrix, you will see the design duty screen. If it doesn't look like this one, this may be showing less detail. So to show the full screen, we can either click here or here. There's a series of buttons along the top. We can either restore the last duty, we can just restore the last units, we can set unit defaults. So we might want cubic meters per hour and millimeters. So we could set those as the defaults. And we can reset, if we've entered some units in here, we can reset all. And because we've set unit defaults now to cubic meters per hour and millimeters, then reset all will restore these units. So let's enter some volume flow. So meters cubed per hour, we might want to put, say, 36,000, and we'll note we get a conversion to cubic meters per second on the right hand side here, so that's 10 cubic meters per second. Now we're looking at actual volume flow, which is the most usual situation. Some consultants may specify normal flow, re 0 degrees C, or there are some other options here, or we can specify a mass flow. So if we specify mass flow, then kilograms per second, the unit options will change here. But obviously we want to go cubic meters per second, cubic meters per hour for this particular example. Now let's look at the pressure. We can either put the pressure on the fan inlet or the fan outlet or both. This can be important or it can not be very significant. It depends on the amount of pressure that we're dealing with, particularly on the inlet. And that's because the negative inlet pressure affects the gas density here. So if we were to put, say, 200 millimeters on here, let's do that, 200, and we can see that we've got a change in density from the standard of 1.2. So that will affect the fan selection. The ability of a fan to develop pressure is dependent on this inlet gas density. So let's put something on the outlet as well. We might put 200 on the outlet as well. And we can see then that the fan static pressure of 400 millimeters is going to be used. Now the inlet pressure would normally be negative. So that's the standard condition. It would only be positive if we have some other fan or something else in the system generating some pressure at the inlet to the fan. So the fan is normally sucking through the duct and creating a pressure below atmospheric pressure. So if we have a glance down here in this area, we can see that we're using gauge pressures, and we can see the absolute pressures down here in millimeters, which is the units we've selected. So if we were to go back to 0 here, we can see that this absolute inlet pressure changes with the pressure that we enter here. So let's put our 200 back. We can see the density change here and the absolute pressure change here. Now if we did want to use absolute pressures, we would just check this box and we could enter the absolute pressures at the inlet and outlet. Some system designers may prefer to use this system of absolute pressures. You'll note that we can't enter, or we shouldn't enter, any negative values here. So we see here that we get a warning that the pressure is incorrect. So let's go back to 0. We'll go back to gauge pressures. Pressure's too low, so we're going to go for 200. Now we're back to a reasonable pressure for a fan. Let's have a look at some of these other options that can affect the fan selection. The selection temperature here can be specified by the system designer, or it may be at ambient conditions. If it's a hot climate, it may be, say, 35 degrees C. That will also affect the density. The maximum inlet temperature here should always be set higher than the selection temperature, and this is for the mechanical design of the fan. This in some cases could be quite high. The system could be designed based on a lower temperature, and it may have occasional excursions to a much higher temperature. So we could put such a high temperature in here, maybe 250 degrees C. You'll notice that the maximum inlet temperature does not affect the inlet gas density because that is dependent on the selection temperature. So let us put that back to 55. The cold start temperature, when the fan is first started, it's going to be usually drawing cold air, the ambient air, and if it's in winter that could be a very low temperature. It may be 0 degrees C, for example. Now, because that will affect the density at the startup, it will affect the amount of power that the fan draws, so it is important that we put the correct cold start temperature here. We can also enter an elevation. We could say the fan is at 100 meters, which also changes the density here. We can also change the relative humidity, which is the amount of water vapor in the air, and we can change the specific gravity, which is a factor, which is the same as relative density, which is for different gases other than air. So if it's a heavy gas, it might be 1.2, or if it's a mixture of light gases, it could be less than 1. And these will all also affect the selection density, of course. So for a heavy gas we might put 1.1, and we've got now a high inlet gas density. So 1 is the standard, which now gives us a much lighter gas density. Now often a system designer will specify this density, so we can simply check this box here and say that it's 1.2, which was the figure specified by the designer. So now we can go on to click Next and select Accessories.